Hello everyone. Today, I, Anand Choudhary from BTech Engineering Physics 3rd year at IIT Roorkee, would be talking about my own solution for automated speech therapy, which has been developed by using the 8085 microprocessor. To begin with, let me give you a brief about what speech therapy is all about. Speech therapy is essentially the assessment and the treatment of many communication, speech, and language disorders, such as articulation disorders, wherein a person is unable to properly, that is clearly and distinctly form certain word sounds, for example, sounds while pronouncing vowels or consonants, or fluency disorders which affect the flow and the speed of a person's speech, for example, stuttering, and dyslexia, which is characterized by slow or slurred speech due to an inability to control the muscles which are used for speaking. And dyslexia is essentially commonly seen in people suffering from nervous system disorders, for example, in people suffering from Parkinsonism. Speech therapy is generally performed by experts in this field, referred to as the speech language pathologists, also known as the speech therapists. Now, speech therapists first of all go about manually examining and assessing a person suffering from a speech or a language disorder. Then they would be checking for the person's enunciation of words or numbers or characters and finding out as to whether that is correct or not. And wherever there is any given possible error in the enunciation, they would possibly suggest appropriate breathing exercises, muscle strengthening exercises in order to improve the speech of the person. And this particular process is an iterative process which would essentially be going on until there is a significant improvement in the person's speech. If this particular process is essentially performed manually, then it is going to take a lot of time. Is there any way in which we can minimize the amount of time which is spent in any one part of this particular process? That is, can we possibly automate any given portion of speech therapy? Yes, we can. As we have said, in speech therapy, there is a need to check for the correct enunciation of words or numbers or characters on a regular basis. It in fact turns out that this particular process involved in speech therapy is automatable. And then once we obtain these results, the speech therapists can essentially analyze the results and on the basis of their analysis, suggest appropriate breathing exercises, muscle strengthening exercises, etc. This, in fact, is better to be done by speech therapists because this involves some kind of a sophisticated amount of analysis which cannot possibly be deciphered by the machines by just being trained on a small amount of data. Consequently, automating a particular process and using humans to perform a sophisticated level of that particular process can possibly lead to a synergistic combination of humans and machines which can accelerate the process of speech therapy like never before. Now that you have an intro about speech therapy and the model that involves an automation element as well, let us now dive deep into my automated speech therapy model, which essentially is the automation of this particular first portion of speech therapy. In my automated speech therapy model, following is the flow of the model. A particular person suffering from a particular speech or speech disorder would essentially be speaking through a microphone, and the obtained noisy electrical speech signal equivalent to this sound signal would essentially then be filtered in order to yield the clean electrical speech signal. This clean electrical speech signal would then be passed through a spectrum analyzer and a peak voltage detector in order to finally obtain a single value of voltage, which should be given as input to an analog to digital converter, which is interfaced with the 8085 microprocessor, which is further interfaced with an LED array. The number of the LEDs which would essentially be flashing in this LED array, for this particular purpose of the model, I've only considered 3 LEDs, though this can be increased as well. The number of the LEDs which would essentially be flashing would thus be an indication of the amount of the correctness in the enunciation of a particular word or a number or a character as done by a particular person suffering from a speech disorder. This flashing of the LEDs would thus in turn via this particular entire model help the person to understand as to what is the level of the correctness in his or her speech. Now, let us examine each and every one of these components of the model in greater detail. In the first part of the model, we essentially have a microphone, first of all, and this microphone is a transducer, which would essentially convert the sound into an electrical signal. This electrical signal would be noisy because of the inherent noise in this transduction process that the microphone carries out. A noise filtration system would then essentially be used in order to clean or denoise this electrical speech signal. This clean electrical speech signal would then be passed on to a spectrum analyzer, which would perform an analysis of the dominant frequencies, harmonics, and other spectral components present in this clean electrical speech signal in order to essentially figure out a particular unique characteristic value of the voltage pertaining to a speech signal referring to a particular word or a character or a number. This particular voltage value, which is a unique characteristic of a particular word or a number or a character, can then be picked up and detected and stored by a peak voltage detector, which would then be used as an input to the ADC. The process of analyzing the spectrum of the speech signals and finding out that particular unique characteristic value pertaining to each and every given word or a number or a character that can possibly be spoken by a particular person is an iterative training procedure. However, once this has been done, there is no need to use a spectrum analyzer, and we can instead use another kind of circuitry which would figure out that particular unique characteristic voltage value, and then that would be detected by this peak voltage detector, so as to finally pass on that single voltage value to the analog to the digital converter. Let us now move on to the second part of this particular model, wherein we would be talking about the analog to digital converter and its interfacing with the 8085 microprocessor. First of all, what is an analog to a digital converter? An analog to a digital converter, also referred to as an ADC, converts an input analog voltage signal into a digital output signal in the form of bits, zeros and ones. In order to analyze the interfacing of an ADC with the 8085 microprocessor, I've considered the ADC 0809 as an example, and it is an 8-bit ADC. And it uses a successive approximation conversion technique, wherein it essentially employs a binary search algorithm for comparing an input analog voltage value against all possible 8-bit binary values in a successive manner, so as to finally converge on the best and the most suitable digital data output corresponding to that particular analog voltage value, and thus it affects the analog to digital conversion. Due to various incompatibilities, however, between the ADC and the 8085 microprocessor, which would be the speed incompatibilities, because the ADC is quite slow as compared to the microprocessor, and given electrical or bus incompatibilities, there is definitely a need for an external programmable peripheral interface, and the 8255 does this job for us. Now let us move on to the interfacing of the ADC with the 8085 microprocessor. In order to interface the ADC with the 8255 with the 8085 microprocessor, with the 8255, we first of all are required to configure the 8255 in a particular mode. In this particular process, it is required that port A and port C upper be configured as input ports, and port C lower and port B be configured as output ports. I will be talking about the configuration of the 8255 in a moment. However, once the 8255 has been configured, the 8085 microprocessor would essentially be sending the SOC signal, or the start of conversion signal, to the ADC via the 8255 in order to enable the start of the analog to digital conversion process. Once the ADC has completed this conversion process, it would send the EOC signal to the 8085 via the 8255. Essentially, the start of conversion signal and the end of conversion signal are nothing but handshake signals, status signals, which are exchanged between the ADC and the 8085 microprocessor. The digital data then can be finally read by the 8085 microprocessor from the ADC via port A of the 8255 when the output enable line goes high. Let us talk about the 8255 in order to essentially figure out as to how to go about configuring the H255 in the first place at all. The 8255 is a commonly used programmable peripheral interface which consists of 24 I/O lines which have been primarily divided into two 8-bit ports, port A and port B, and the third port is port C, in which we can use its bits, 8 bits individually, or we can use it as two separate 4-bit ports. The 8255 can essentially enable the transfer of data between a peripheral device and a microprocessor in various operational modes, ranging from the simple I/O mode to the interrupt I/O mode and to even the bidirectional data transfer mode, wherein port A can actually act as an input as well as an output port. Furthermore, it is important to note that the 8255 is quite flexible and versatile in its operation, and in order to communicate with the peripherals via the 8255, first of all, we are required to essentially determine the addresses of these ports A, B, and C, and that of the control register as well, which is essentially going to control the operation of this 8255 by noting the chip select logic and the bits carried by the address lines A1 and A0 of the microprocessor. For this particular example, the chip select line would essentially be low whenever all lines from A7 to A2 are essentially low, and then depending upon the bits carried by the lines A1 and A0, we note that whenever A1 and A0 are both going to be 00, the hex address would be 00H, which essentially corresponds to the address of port A. Similarly, whenever A1 and A0 are carrying the bits 0 and 1 respectively, then the hex address would be 01H, which corresponds to the address for port B. Then we go on to the address for port C, which is 02H, and finally the address for the control register, which would be 03H. This address is important to note because it would be used in the first place for configuring the 8255. After we have essentially determined the addresses for all of these ports in the control register, the next step is to write the appropriate control word in the control register of the 8255 in order to specify the mode of operation of the 8255. Once we have written the control word, the format of which is given over here, we can then move on to write I/O instructions in order to communicate with the peripherals via the 8255. Let us now discuss the ALP for interfacing the ADC with the 8085 microprocessor. To begin with, this is a small snippet of the code which only contains 2 lines. I've pasted it over here in order to show as to how this particular hex number 98H actually corresponds to which configuration of the 8255. 98H essentially corresponds to this particular control word 1001 1000. Essentially 1 at D7 is equal to 1 indicates that we are setting the IO mode. Then we note that Group B and Group A ports are essentially in mode 0, which means that it is a simple IO mode wherein ports A, B, and port C upper and C lower can function as either an input port or an output port, and port A and port C upper, as we've already discussed, have been configured as input ports over here, whereas ports B and port C lower have been configured as output ports. Let us now examine the entire ALP in greater detail. Once we have then initialized the 8255, which I have just discussed previously, we are required to then move on to select channel 0 of the ADC in order to essentially take in the voltage value as input from channel 0 of the ADC. Once that has been done, the 8085 microprocessor will essentially be sending the start of conversion of the SSE signal to the ADC via the H255. Once the conversion process is complete, it would receive the end of conversion signal. But the 8085 microprocessor essentially needs to check whether it has received the end of conversion signal. As I had previously shown in a diagram, for this particular example, the end of conversion signal is essentially obtained via the PC4 line, which essentially belongs to the C upper port of the 8255. Consequently, we are going to essentially mask the other bits, and we are only going to essentially consider the PC4 bit of the C upper port, and whenever it is high, we note that the resultant value of this ANI operation, which essentially just performs the logical AND operation, and thus it would be high only when both when the PC4 line is high, that is the end of conversion signal has been obtained from the ADC, then in that particular case it would essentially generate a non-zero value, and then it would exit this loop of continuously checking as to whether it has received an EOC signal or not. Once the EOC signal has been received, as I described earlier, the output enable line needs to go high, and then you can easily read the ADC's output data from the port A. Once the 8085 microprocessor has read the output data of the ADC via port A, it is going to store the data in a memory location temporarily. This is needed because then this particular data is to be compared with the correct enunciation of that particular word or number or character. Now, it is necessary to also take into consideration the limitations involved whenever we are dealing with ADCs. Ideally, we would expect the graph of the digital data output versus the analog input voltage to be a straight line, such that we get a unique value of the digital data for every given corresponding possible value of the input analog voltage. However, it turns out that this is not the case in reality. What we actually get is the fact that we observe a single digital data value for several possible values of the analog input voltage value. And this is essentially because of a limitation in the smallest possible value that the ADC is capable of resolving. And this is referred to as the resolution of that ADC. Considering the 8-bit ADC 0809 and considering the input voltage range to be from 0 to 5 volts, the resolution would be the maximum analog voltage divided by the total number of the binary numbers that can possibly be represented by the ADC in its digital data output. Considering the case of an 8-bit ADC, we find that it is 2 raised to the power 8 numbers in total from 0 to 255, that is from 00H to FFH, which is equivalent to 19.53 millivolts. Consequently, we note that we would essentially be obtaining the same digital data output for every interval of a width 19.53 millivolts. This results in the digital versus analog graph taking the form of a staircase comprising of shifted step functions. Furthermore, we note that fluctuations would be observed at the transition points of the graph, and this is essentially because of the fact that the ADC can only output a number that is either n or n plus 1. However, it cannot output a number which is in between. And furthermore, we can add to all of this the effects of noise, and therefore the graph that we actually obtain in reality is somewhat like this. What is the solution to all of this in our solution? Because this inherent problem of resolution can pose to be quite a limitation when we are dealing with a large number of words. We may not be able to essentially encode a large number of words in it all. The solution is to use an ADC with as high a resolution as possible. Considering the case that the 8085 microprocessor can only possibly deal with 16-bit numbers at a time, we use the 16-bit ADC, which is possible of encoding the values from 0000H to FFFFH, and then we calibrate the words and the voltage values accordingly. Furthermore, the fact that we have the same digital data output corresponding to a set of input analog voltage values, it is advantageous for us in this application over here, because a particular word can correspond to numerous analog voltage values within a small range, because different people have different enunciations of the same word, and all of them could possibly be correct. Then for all of those voltage values, as desired, we only have a particular digital data output value, and then that can be compared against a single correct enunciation of that particular word. Let us now move on to the final part of this automated speech therapy model. That is, once we have essentially stored this particular representation of this voltage equivalent of the word, the number of the character spoken by the person suffering from a speech disorder in a memory location of the 8085 microprocessor, we are required to essentially compare it with the correct enunciation of the word and figure out whether the difference between the spoken word and the correct enunciation of the word are essentially going to be nonetheless the same within a specified level of tolerance. So maybe we can even go on to specify more than a level of tolerance, as I've done in this particular case over here. In order to do this, it is necessary to write an assembly language program for the subtraction and the comparison of two 16-bit numbers. First of all, I will be discussing the assembly language program for the subtraction of the two 16-bit numbers. In order to effect the same, we first of all required to load the HL register pair with the contents of memory locations 2005 and 2006. As you might recall, the output of the ADC, that is in fact the digital data output, was stored in the memory locations 2005 and 2006. That was essentially corresponding to the spoken word or the number of the character by that particular person suffering from speech disorder. In order to compare it with the correct enunciation of the word, we are required to retrieve it now from that particular memory location, and in order to do so, we load the HL pair directly using the LHLD instruction, and essentially in this particular case over here, the lower order memory location would essentially contain the lower order byte, which would then be stored in the lower order register, that is the L register, and the higher order memory location would contain the higher order byte, which would essentially go into the H register. Once we have essentially got the spoken word, the number of the character, we are also required to get the correct enunciation of that particular word. In order to do so, we are first of all required to essentially exchange the contents of the HL register pair with the D register pair, such that the spoken word or number of character goes into the D register pair. Then we can, in a similar manner, load the HL register pair with the contents of memory locations 2007 and 2008, which should essentially contain the 16-bit number corresponding to the encoding of the correct enunciation of the spoken word or the number of the character. Once this has been done and we now have both the numbers in hand, we are required to perform the subtraction of these two numbers in order to determine first of all the difference. Only then can we move on to compare the value of the difference against all possible tolerance values, in order to figure out the level of the correctness in the enunciation of that particular word or number or character by a particular person. Now in the 8085, although we have an instruction already predefined for the addition of two 16-bit numbers, which is the DAD instruction or the DAD instruction, there is no such equivalent instruction for subtraction, and consequently we need to write an ALP for performing the subtraction as well. In order to do the same, first of all, we would be performing the subtraction of the lower order 8 bits of the two 16-bit numbers, and whatever borrow is going to be generated from the subtraction of the lower order 8 bits of the two 16-bit numbers is essentially going to be then passed on, and then this particular borrow is going to be utilized in the subtraction of the higher order 8 bits of the two 16-bit numbers. This is finally then going to result in our 16-bit number subtraction. So first of all, we are going to copy the contents of register E into the accumulator. Then we move on to subtract the contents of register L from the contents of the accumulator and save the resultant difference in the accumulator. Now this might possibly generate a borrow, and that is fine. We note that because this instruction is essentially going to perform the lower order 8 bits of the numbers, which have been stored in the D register pair and the HL register pair. Once this has essentially been done, since we are required to store the final resultant difference in the HL register pair, we copy the contents of the accumulator into register L. This is the result of the subtraction of the lower order 8 bits of those 16-bit numbers. Similarly, we move on to perform the subtraction of the higher order 8 bits. The only difference in this case is that instead of the SUB instruction, we use the SBB instruction, wherein we are also required to take into account any given borrow that has essentially been generated from the subtraction of the lower order 8-bit numbers. Once the subtraction process has been complete, we are then required to store the difference of the higher order 8 bits into the H register, and then the H register pair would essentially contain the resultant difference between those two encodings of the spoken enunciation of the word and the correct enunciation of the word, and then we move on to store the contents of the HL register pair, that is this resultant difference, in memory locations 2009 and 2010, again with the correspondence as earlier, with the higher the byte stored in the higher order register going to the higher order memory location, and that in the lower order register going into the lower order memory location. L, as we've already noted before, is the lower order register and H is the higher order register. This would essentially then be helpful in comparing this particular stored value of the difference against all possible tolerance values. For the purpose of this particular model, I've essentially considered three possible levels of tolerance. First of all, we will be moving to compare the difference, the value of the difference with the first tolerance level. In order to do so, we are required to definitely first of all load the value of the difference into the HL register pair. Then we are required to exchange the contents of the HL register pair with the D register pair. This is done so that the D register pair essentially stores the value of this difference, and then the HL register pair can possibly store the value of the tolerance level. The tolerance values which are specified in this particular case are essentially 0005H as the first tolerance level. Second tolerance level is 000AH, which essentially corresponds to 10 in the decimal number system. And finally, the third tolerance level which I have used would be 000FH, which is essentially corresponding to 15 in the decimal number system. Now, in order to compare the tolerance value against this particular difference value and figure out as to whether this particular difference is lesser than or at most equal to this particular tolerance value, because only in that particular case would we be lighting the appropriate LEDs, we are essentially required to perform the subtraction of these two 16-bit numbers. This proceeds in the same way as I have described earlier, and once the subtraction has been performed, we would be able to obtain the value of the difference between the resultant difference which was generated between the correct enunciation of that particular word and the word as spoken by that particular person, and as compared against the tolerance level 1 over here. Now, whenever the subtraction is performed, then in that particular case, 3 cases may possibly be observed. Now, if the value of this particular difference, whatever we have computed over here and is stored in the HL register pair between the tolerance level and that resultant difference obtained earlier, if that particular value is essentially going to be, if this particular difference, resultant difference value is going to be less than the tolerance level value, then we find that it is essentially going to generate a carry. And if it generates a carry, we would be lighting up the required LEDs. In fact, even if it is the same as that of the tolerance value, in that case it would essentially set to the 0 flag, even then we would essentially move on to light the appropriate LEDs. However, if it does not set the 0 flag, or it does not set the carry flag via any given generation of borrow, then we would essentially be moving on to check the second tolerance level and other subsequent tolerance levels as well, and that would essentially be done by noting the fact that whenever this resultant difference is greater than the tolerance value, then it would be resetting the carry flags and a carry flag as well as the 0 flag, because it would neither generate a borrow nor would the result be 0. Consequently, when we have checked for this particular 0 flag and we found that it has generated a 0 flag, since 0 flags and carry flags are separately set or reset and are not set or reset simultaneously, once we've checked for the 0 flag and we found that it has been set, it is necessary to set the carry flag so as to avoid any given possible checking of the tolerance level 2. Consequently, we find that once it is essentially passed both of these conditions, that is once it is passed either of these two conditions, that is, it is either set the 0 flag or it is set the carry flag, that is essentially generated a borrow, then we move on to light the required LEDs. In this particular case, since the tolerance value is quite small, we find that the person's enunciation of that particular word is quite close. It is in fact to the actual or the correct enunciation of that particular word, and therefore it is excellent. In that case, we would be lighting up all the 3 LEDs, and the LEDs would essentially be lit up by providing this particular data byte over to this particular port of the ADC H255 microprocessor, wherein we have essentially connected a decoder and further on a latch in order to light up the required LEDs, and an LED would essentially be lit up whenever it is provided with a 1. Consequently, we note that the binary equivalent of 7 is essentially 0111, and therefore the 3 LEDs would essentially be lit up. Once the LEDs have been lit up, then we can stop the processing of the program and terminate the program. However, in another case, if either of these two conditions is not satisfied, then we move on to essentially check tolerance level 2. In tolerance level 2, the same procedure will essentially be involved. Only the case is that the tolerance level 2 is now a bit higher than the first tolerance level. That is, it is now going to be 000AH. And once we find that this that the resultant difference between the correct enunciation and this of the word and the enunciation of that particular word as done by the person suffering from the speech disorder is more or less the same, then in that particular case we are going to light up only 2 of the LEDs, because this indicates a good performance as regards the speech of that particular person. So in order to light up 2 of the LEDs, we would essentially be required to provide 2 ones as bits, and consequently that corresponds to the code 03H, and this is given to the output port 00FAH as before. Then we note again, as in the previous case, that if tolerance level 2 is not met, then we go on to finally check tolerance level 3. In tolerance level 3, we check with an even higher tolerance value, that is about 000FH, and in case the difference lies within this tolerance value, then we would be only lighting up 1 of the LEDs, because this tolerance value is quite high, and therefore the person has demonstrated essentially an average kind of a performance as regards the enunciation of a particular word or a number or a character, and this can easily be done just by providing a 1 on the last line, and that would correspond to 01H, and this is given to the output port 00FAH. Finally, when we check all of these tolerances, and in the case that none of these tolerance value conditions are met by the resultant difference, we move on to the condition wherein we are not going to light up any given LED at all, which essentially signifies the fact that the given person suffering from the speech disorder needs improvement. Once all of these checking procedures have been completed, then we would be finally stopping the processing of the program and terminating the program. In order to illustrate the execution of this particular ALP, let us consider an example. Let the correct enunciation of the word happy. I'm assuming over here the person who is suffering from speech disorder is checking his or her enunciation of the word happy. So let the correct enunciation of the word happy be represented by 5005H, and the corresponding transformed spoken word be 500AH. Essentially, this is the enunciation as done by that particular person suffering from the speech disorder, and this, as has already been indicated, is the correct enunciation. Consequently, the difference between the two is only 0005H, which is equivalent to the tolerance level 1, and therefore the person has demonstrated an excellent level of performance as regards the enunciation of the word happy, and therefore all the 3 LEDs would essentially be lit up. So we are going to be providing the following inputs for subtraction. As has already been indicated in the case of 16-bit numbers, the lower order byte would essentially go to the lower order memory location, the higher order byte would go to the higher order memory location, and this is what has been done over here. Finally, we will be storing the difference, as had already been indicated, with the SHLD instruction in memory locations 2009 and 2010, which in this case should be 0005H. Once this has been done, we are required to essentially transfer the data byte 07H onto the output port, so as to essentially light all the 3 LEDs. Let us check as to whether our code yields the desired results or not. As can be seen in this particular snippet of the code, on executing the set of the first 3 instructions, we find that the enunciation of that particular word is spoken by the particular person has been stored in the D register pair, and the correct enunciation has been stored in the HL register pair. Then we move on in order to essentially perform the subtraction of these 16-bit numbers. Once we have subtracted the lower order 8 bits of the 2 numbers, which were essentially 0AH and 05H, there will be no borrow which will be possibly generated in this particular subtraction, and consequently 05H will be the data byte stored in the L register. Then we are required to move on in order to perform the subtraction of the higher order 8 bits of the 2 registers, and on doing so, we would definitely be obtaining 00H. Once we have essentially obtained this particular result in difference value, we can then move on to compare it against the possible tolerance values, and in this case it is evident that this falls within the level of the tolerance 1, and consequently we should be able to light all the 3 LEDs in this case. Let us see if that is actually the case. Now we are essentially required to load in the tolerance value as well in this HL register pair, which as you can see has now been loaded over here. It is 0005H, and previously also we could also note that we have also stored the contents of the HL register pair in memory locations 2009 and 2010, as can be seen over here. This is nothing but 0005H with the lower order byte being stored in the lower order memory location and the higher order byte being stored in the higher order memory location. Now, once this has essentially been affected, we are then required to compare this resultant difference value with the specified tolerance value in order to see whether the difference falls within this tolerance value or not. So as done before, we are required to perform the subtraction of these two 16-bit numbers, which clearly generates the resultant value as 0000H. Therefore, it sets the 0 flag. This clearly indicates that as desired, our resultant difference falls within the tolerance value, and therefore we are required to light up all the three LEDs by providing 07H to the output port by storing it in the accumulator, and then essentially outputting it by the out instruction on this output port specified with the address FAH. Once this has been done, you can clearly see that the FH port now essentially contains its data byte 07H, and thus all the three LEDs corresponding to the last order lines of this particular LED setup would essentially be lit up as desired. Thus, our assembly language program has been executed successfully, and our automated speech therapy model proves to be a success. Finally, I would be discussing in brief about the advantages of my automated speech therapy model. It is evident that automation would lead to faster and more accurate speech analysis. It would be definitely relatively cheap to manufacture, considering the fact that the spectrum analyzer is only needed in the initial training procedure of this particular entire part 1 of the system, as it already been described earlier. Later on, we can replace it by any other given circuitry that directly isolates that particular unique characteristic of the clean electrical speech signal, and then we can just detect that particular unique peak voltage value with the help of a peak voltage detector. Then there is also a possible control over the number of the words or the number of the characters which can possibly be stored in the 8085 microprocessor, because we have a certain number of the memory locations which we can possibly use in the microprocessor with the same purpose. And an added advantage over here is that it is also possible to store words in different languages via different encodings, because we can derive essentially encoding schemes of our own, and thus this particular case can serve the need of the people across the entire world. I thus believe that this automated speech therapy model that I've developed can prove to be revolutionary, and it would be an interesting experiment to be able to implement this in practice and try it out as to how it finally works. Thank you.